we're actually going to talk about a different tool, which is SimSolid. SimSolid is an analysis tool. It's meshless in what we think about a traditional mesh being, and that it's discretizing your parts in a different way. It's discretizing them either via point clouds or features or on the part level. We're going to apply our loads and boundary conditions on this original CAD geometry. And the goal here is to allow us to be able to look at very large assemblies and complex parts without all of that overhead that traditionally comes in model setup. Typically, setup is where we spend most of our time in traditional FEA. By cutting out a large part of that, we can spend more time on the analysis and the post-processing and really understand our designs better. We'll talk a little bit about how this works. It basically goes through this adaptive process and refines the solution over different iterations. And it is fast. That is the main draw to SimSolid, is being able to do these large assemblies very quickly. As far as where this falls, it's not necessarily always that SimSolid is going to replace your traditional FEA solver. In some cases, that may be true, and in some cases, we can use it to supplement our existing tool set, be able to run quick analysis, and then maybe do our final validation in traditional FEA if that's what we want to do. All right, better than talking about it in the 15 minutes that we have, it would be wise to just go ahead and go through an example. This is the interface. We can import from a file. We're just going to import a skid model. It takes sometimes a little bit of time to read in, and that's because we are on import actually bringing in and categorizing these different parts. So this was just a parasolid file, but based on the geometry, SimSolid brings us in and says, oh, this part's a nut, this part is a bolt, this is just a generic solid, and that helps the solver later on. So we do the classification up front. Different ways to view this, but as someone coming from those kind of traditional pre-processing tools, HyperMesh, I like all of the colors. This assembly has, let's take a look here, 376 parts. And there's a lot of checks in here when you bring this in, things like being able to review the parts, check the geometry for defects. A lot of times when you run into solution problems, it'll be because the geometry that you brought in had some issues with it. But in general, don't have to do a lot of geometry cleanup here. As opposed to removing every single small intersection, you'll actually notice when you go to the geometry checker that it will tell you what kinds of overlaps and such you have. These small overlaps are going to end up being acceptable. The solver is going to be able to handle this so long as they're brought in as separate parts and not as one big merged component. All right, so the first thing we'll do here, come up and set up connections. There's this auto connection tool to find parts that are within some kind of gap and penetration tolerance. I'm going to start here with 1 millimeter gap and penetration tolerance. We typically recommend starting on a normal connection resolution level. I've looked at this model prior to this, so I know in this case I'm going to need some increased resolution on the connections. This is not a particularly large assembly. In general, we'd recommend going in and increasing them only where it's needed, but for the sake of time here, we're just going to increase them on all of the connections. It's going to come through and evaluate the connections. By default, everything in here is going to have a bonded connection based on your own experience and how you want to set up this problem. You can certainly come in here and edit the contact conditions. So separating or being able to do sliding contact. And you'll notice when we scroll down that some of these already have sliding contacts associated with them. That is because we have special connection definitions for connectors like bolts. So if we show all of the connections that it made, for instance, here at the intersection between these two parts, that is just going to be a bonded connection. But when we go over to the bolts, you'll see some certain yellow sections here where sliding contact has been enabled based on that special connector entity. Before I set up my loads and boundary conditions, I'll go ahead and apply materials. There is a built-in material database, so you're welcome to use those. You can also add your own materials. You can set up a material database that's specific to your company and share it with everyone so that everybody is working off the same set of materials. I'm going to go ahead and apply steel to all of this and say this is just a generic steel assembly. We'll talk about some of the different analysis types that are supported in SimSolid, but for starters, we will just set up a basic linear static analysis. I'm going to set up and constrain the bases in all the degrees of freedom. And then also this little ladder piece. And then come in here and apply a force as if someone is standing up here on this platform, or maybe even a couple people. Maybe he's got friends. And they're both going to stand over here together. Put 2,000 newtons worth of force there. And now let's talk about some of the different solution settings that are available. The default here is going to be adapt for stiffness if I just want to look at kind of global displacements and global loading. If I want to do an actual stress study and look at detailed stresses, this is going to change the number of adaptive runs that are done. And in setup, if I am interested in looking at a nonlinear solution, I can specify what kinds of nonlinearity are going to be in the problem. You will notice that some of them you can't kind of cross-pollinate with each other, and you will see that if you click OK, it will guide you through what's supported. So in this case, it'll say geometric nonlinear with separating contact not yet supported. Like I said, we're going to keep this as a linear static analysis. Click Run. You'll notice in the background here, it tells you what's going on. So the first thing is it's going to evaluate the geometry, go in and characterize all of these things. Then we're going to analyze the connections, and then it's going to do 3 different physics passes where it analyzes the areas that need higher refinement, goes through, and in this case, because we have done adapt for stress, we're going to go through and do 4 different passes, and then at the end there'll be a step for, I think it's called like contouring results or processing results. While this is running, let's go back to the slides for a minute, and let's talk about the question for a moment. Designer-oriented software, specifically in this case, talking about SimSolid, is it accurate? The real answer is, for the right problems, it's a very good and very fast solution. Not every problem is the right problem to throw at SimSolid. But perhaps more objectively, NAFEMS did a study on designer-oriented software and tried to benchmark different meshless solutions compared to each other. I'll send that along in the link, and you can read for yourself some of the test problems they did, how accurate it is. The general summary here, though, is it is giving accurate results that are comparable to traditional FE analysis. Let's come back over here. This is finished running. You can always ask it for the different stats about it. So in this time, runtime, 1 minute, 30 seconds. First, take a look at displacement. The standard outputs here, displacement, stress, strain, and so forth. Within here, let's take a look at the animation. Just as a heads up, this is always scaled by default so that you can kind of see the general motion happening. If we want to do and look at the actual magnitude of the deformation, we just turn on this true deformation and it won't scale it. This is much more of a kind of sane outcome, or what we'd hope for some structure that somebody's going to be standing on. And when we go and look at the contour here and the max displacement, we're at a fraction of a millimeter. So this whole structure is not, in fact, falling off or warping. We can also look at different stress plots. If I had done multiple setups here, you can jump between them pretty easily just by clicking. And My personal favorite is actually this safety factor plot. It's very easy here with just steel to glance at this and say my peak stress is below yield. That, of course, becomes significantly harder the more materials you have. So we come over to safety factor here, and for each material, this has already been computed. So at a glance, we have some understanding of how close we are to yield. Other potential points of interest here, being able to look at bolt and nut resultant forces. Maybe I want to do some post-processing in Excel after this and be able to do some hand calcs. So I can also pull things like axial force in the threads, save it to a CSV, and kind of move on with my life outside of SimSolid. Other things here, you can also look at reaction forces and being able to look at contact forces between all of these, in this case, mostly bonded contacts that have been set up. You're not limited to purely these bonded sliding separated contacts. You can also model welds of different sorts. So seam welds, spot welds. So here is a full list of the SimSolid capabilities, different solution types that are supported. Maybe the most frequently used, if I had to guess for this group, probably nonlinear static, maybe fatigue also, the different connection types, and then these different standard results that are output.